So our next talk is going to be Selvakumar Jawahar. He is a senior software engineer at Juniper Networks, where he builds advanced network assurance tools. In a career spanning 19 plus years, Selvakumar has designed high-performance embedded systems and engineered large-scale enterprise software. He's also designed real-time web applications. He deeply cares about building exceptional quality and high-performance software systems. He enjoys building with C++ the most amongst the many languages that he uses. Now, to give his talk on concurrency with React patterns, here is Selvakumar himself.
Thank you, Anushi. I hope everyone can hear me.
Yeah, we can hear you just fine.
Okay, so I'm Selvakumar, and I work at Juniper Networks as senior software engineer. And my talk today is going to be on Reactor pattern. This is something which we implemented in Juniper. So let's begin. So before jumping into the Reactor pattern, let's get the context. So there are a couple of things I would like to clear up before we start. The first is there is a difference between a design pattern and an architectural pattern. So I highly recommend this book, Pattern-Oriented Software Architecture. It's from volume 1 to volume 4. I highly recommend everybody reading that. So before we jump into Reactor pattern, there are a couple of concepts I want to clear up before we start the Reactor pattern, so that everyone gets a context. So there are design patterns and architectural patterns. And actually, I will recommend this book, Pattern-Oriented Software Architecture. It has volumes from 1 to 4, and it's I would say a must for anybody who is into system design. So this is from this book. So what is a design pattern? So design pattern typically describes a solution to a commonly recurring software problem which has a context and which is well understood problem, and it provides a way to address that problem. So when we talk about patterns, this by default we are talking about design patterns, and this has been popularized by GOF, Gang of 4 book, and the common design patterns which we all use. It's factory, command, strategy, singleton, etc. Now, what is an architectural pattern? So architectural pattern is something which provides a fundamental structure to a software system. So it's a little higher level than the design pattern, and it talks about different components in the architectural in the system architecture and how they interact. So some examples of architecture pattern are layered architecture, or a more common one is MVC and microservices and stuff. So this particular pattern, the Reactor pattern, it's an architectural pattern. So we are going to talk about an architectural pattern. Okay. So, and if you have any questions in the talk, please put them in your Q&A tab, and I will pause in between as we go, and we will see. We will answer. I will try to answer as many questions as possible. So moving forward. So another concept before we go into the Reactor pattern, which is concurrency and parallelism. So concurrency and parallelism, though they are often used interchangeably, and they both are related concepts, but they are actually a bit different. So again, there is a very good talk on concurrency by Rob Pike. If you don't know who is Rob Pike, he's the lead designer of Go, and he's contributed a lot of stuff in Unix. So for me, what I mean by concurrency is something which describes the structure of a system. A concurrency defines how different components of system interact to achieve something, to achieve certain jobs which are run at the same time. So it describes the structure. It gives the model of how different components work and give us a result at running at the same time. And parallelism is mainly focused on the execution. So when I say parallelism, I'm talking about execution. Means we have several jobs running, executing at the same time simultaneously. So that's parallelism. You can have a concurrent system where some concurrent model of a system where some parts are running in parallel and the other parts are not running in parallel, but they are concurrent. So, for example, in a UI, in a graphics application, a graphics application can handle multiple events, like events coming from a mouse, events coming from keyboard, some network events. You can all handle it concurrently while doing some image processing, which is running some parallel algorithms there. So, so concurrency defines the structure of the system to run multiple things at the same time, and parallelism is the execution of multiple stuff. So typically concurrency can happen on a single core processor as well, and parallelism typically requires more than one execution unit. So it could be multiple CPUs, GPUs, which is doing some number crunching, and that's parallelism. So why these two concepts needs to be clear before we start reactor pattern? Because reactor pattern, it's an architectural pattern, and it's for designing event-based concurrent system. So what is reactor pattern is, it's an architectural pattern. So it's going to define the overall structure of the software system, and also it's a concurrent pattern. Means it's going to give how different modules interact to achieve concurrency in a system. So any questions so far?
I see one question in chat, which is from Shashank. He asks if parallelism and concurrency are mutually exclusive.
No, it's not mutually exclusive. So as I mentioned, you can have a concurrent system which has some part running in parallel. Like if you have a UI which is doing some graphic processing, so the UI itself, so it's a concurrent system where the main UI thread is handling the events coming from keyboard and mouse or the user inputs, where the actual graphics processing in that system is running parallel in a GPU. So it's not mutually exclusive. So a concurrency model gives you the structure, which can include parallel designs in. Thank you. So moving forward. So my way of learning any pattern is basically by an example. So this example we are going to see today, and we are going to design today, is of an IoT system. So this is based on something which we did at work. So the core concepts are the same. So let's try to understand this system, and let's try to design this. Okay, so what we have here is IoT system. So an industrial IoT system where basically what it does is it collects some sensor data from different locations and sends it to the central server. In the central server, you can process the data and do some analytics and do some monitoring and stuff. So these edge servers are the servers which are located at the edge. When I say edge, it means the edge of a network. Where so typically these edge servers are located in an industrial system. It could be located in a different plant, production plant or production line, or if you see in some monitoring weather monitoring systems, so it could be located at a certain station. So these are the edges. So and this edge server interfaces with several sensors depending upon your what you are going to measure, and this edge servers then over network send the data to the central server. And there could be hundreds of edge servers distributed geographically at different places, and they all send the data to the central server. The central server then collects the data and processes. So this is a simple, this is a top-level IoT system which we are going to design. Our focus is going to be on the edge server. So let's try and see what goes into an edge server, what it does, and then let's try to come out with a design for this. Okay. So IoT edge, what does an IoT edge look like? So typically in an edge, we have edge server. So this is typically a simple hardware which acts as a router, and then edge server software runs on it. And typically you have sensors which communicate, which sends data to the edge server over some network. So you can imagine a manufacturing plant where you are monitoring humidity, temperature, and some pollution or air quality measurements. And these sensors are located different places in the plant, and these sensors send data to an edge server over the network. What the edge server does is it collects, aggregates all this data, and then it sends this data to the central server. So that's what an edge server does. Okay, so let's see some of the characteristics of the edge server. So edge server is something which located at the edge. As I said before, it's the edge of the network point, which depending upon application could be any geographical location. And all it does is moves data from sensors to central server. Then the important point here is this edge server, it just does an IO operation. Means it just collects data from here and sends it. It does not do any actual processing on the data, because that is done by the central server. It's important as we see, as we try to design this. Okay. So what are some of the design challenges of this edge server? So typically edge server runs on embedded hardware with resource constraints, typically a single core or a dual core CPU. So our edge server, our software should run on this embedded hardware using its resources efficiently. It should handle thousands of data points per second. So as the sensors send data to the edge server, this data, each sensor will be sending data continuously, typically multiple samples per second. And this edge server need to take this data and send it forward. So it should so this is one of the design requirements. Now, the third design requirement is there could be different, though all the sensors send data over network, some different sensors could have different protocol. So the edge server need to be able to talk to the sensors and get the data from the sensors. And lastly, if you want to add new sensors to the system, the edge server should be extensible. I mean, it should not be very too difficult to add new sensors to the system. The edge server should be flexible and extensible for adding new sensors. Okay, so let's try to design this system. I hope everyone is clear on what we are trying to design, understand what are the challenges or requirements of the edge server. Any questions? Okay, let's proceed. Please put in any questions if you have. Okay, so now let's try to design this system using threads. So one, so a basic design. Sorry, I think there is a question.
Yeah, it looks like there's a question. Shashank asks, what kind of protocol for sensor to server communication?
It could be anything, but typically the servers send data over UDP, and it continuously sends data over UDP to reduce the latency. And the actual application protocol inside the UDP are typically very specific to the sensor used. So but on the network, it's mostly TCP. But it could be anything actually. Okay. So in a typical thread-based design, okay. Before we go into that, we can also see this. Look at this edge server and this sensors in a different way. We can also say that this is a generic server, and these sensors are clients. So you can have, so this is like a generic web server or any other server, and there are clients which are connected to the server for some resources. So this particular design which we are going to do will also be generic enough to address any concurrent server. So, and one typical approach, and I think several not new but several old libraries, in fact several Java libraries use this kind of application, this kind of design where you have one thread per connection. So let's try to design the system using threads. So so we have this edge server application. So you have a connection manager. So the idea of this design is whenever server connects, there is one thread per connection. So there is a thread pool. The server connection manager establishes the connection. It uses a thread from the thread pool, and the thread takes care of the communication with that particular sensor and writes the data into some shared memory. So, and then there is another thread which runs a server broker, which reads from the shared memory and writes the data to the central server. So this is a very common commonly used design for a server-client communication, where we have a thread pool which manages the connection, and you collect the data. So now, there are certain key things here to notice. The first thing is there is a shared state. I mean, I mentioned here shared memory, but this is not necessarily the actual Linux shared memory. It could be any shared state which is used to communicate, used to get the data from the client threads to the server thread, server broker thread, which sends the data to the central server. Okay. So, okay, I think I have another question. Yes, a question from Manoj, which is shared memory represent DB files. Sorry, I think yes, that's right. When I say shared memory, I mentioned I mean there is a shared state. It could be actual shared memory, Linux shared memory, or it could be anything. A file or DB would be a file would be not a good choice, but a DB, yes, it could be. So there is a shared state where threads write into, and then a shared broker which basically reads this data and sends to the central server. This design from the top level, it looks simple, and it's kind of many places this similar design is used, where it's a thread and you handle the each thread handles a connection. But there are certain drawbacks with this approach. So let's see some of the drawbacks. So in our company, when we first started to design this concurrent system, the first approach, of course, was to use threads, and though not one thread per connection, we were trying to use a thread pool and trying to align the number of threads with the number of CPUs available, so that it's a bit optimized. But even then, the problems which I'm going to mention now will occur. I mean, we will have to face those, even if you don't do a one thread per connection. So the first problem is the code complexity. So when you start using raw threads, when I say raw threads, means something like pre-thread or any equivalent, without any higher level abstraction, and you start using raw synchronization primitives like mutexes and stuff, the code basically becomes more hard to read, and when it becomes hard to read, it's hard to reason about, and it becomes more error prone. The other problem is there is a challenge to prove the correctness of the design. So it's very hard to say that there are no race conditions here, and as the code becomes larger, and this problem actually starts growing bigger and bigger. The other problem which leads to code complexity is the testing. So there could be there are several times what happens is in a normal testing, thread-based design works fine, but in actual production, it starts going into some race conditions or something, because it's the design itself is a bit complex, and maybe it's not very thought through. So the first problem is code complexity. The second problem is performance. Surprisingly, you may think that with multiple threads, you have concurrency and you have better performance, but not always. Because whenever thread switching happens, there is a context switching, and there is a cost you pay for that. And the performance becomes more noticeable. The performance degradation becomes more noticeable when you have single core. Then it's kind of, then it becomes quite bad if you're not very careful. The third is extensibility. So we talked about how the ease of adding more support for different sensors. Here it becomes, it's not very straightforward to add support for more sensors, because now you have to think about what kind of, so you have to think about what will happen if you're running that particular sensor in a different thread, and how to spawn and how to manage that. Whether it will affect some other shared state, because you are having a shared state there. So extensibility becomes a problem there. So what can we do about this? And of course, in our case, we had another problem that some systems where we want to deploy our software does not support thread. So, its thread was kind of a no-go. But even with even if you have support of thread, you have these problems which you will have to deal with. Okay, so let's see what we can do about it. So now comes a reactor pattern to a rescue. So reactor pattern, what is, now let's try to formally define reactor pattern. So yes, I think you have another question. Okay, the question is, in this scenario, does there exist a continuous data connection between sensor and edge server, or it's like once every few hours or days there is communication? In our scenario, it was continuous data. I mean, every second there were like from 10 to 100 data points. So every millisecond there was a data. So there was a continuous data. But this system can take care of even if it's once. So that because of the continuous data, the problem. So it poses certain other challenges. But even if you have continuous data, or the data is like once every few hours, reactor pattern, which we'll go into now, kind of fits in both cases. So yeah, let's see what reactor pattern does. Okay, so reactor. So this is the formal definition of reactor pattern. This is mentioned in this volume 2 of this pattern-oriented architecture book. Do not get intimidated by this difficult definition. What it actually means is, so React pattern, it's for any event-driven application. What it does is it waits for the events, and it looks at the event, calls the particular event handler sequentially. So that's what the reactor pattern does. So there are multiple clients who are sending events to the system. The reactor waits for those events and takes events coming in one by one and handles them. So let's see some examples of how to do this. So these are the different components of a reactor. So you have this application, which has an application core, and you have a reactor. So let's first see what are the different components in a reactor. So the main component of the reactor is the synchronous event demultiplexer. What this does is, this is the module which kind of blocks and waits. It's synchronous, means it blocks the execution and waits for the event. So whenever there is an event, it will demultiplex it. What I mean by demultiplex here is, there are multiple events coming in. It will take the events one by one, and then it will basically provide the reactor, the other component, the reactor interface, that this particular event has occurred with that particular handle, and then this reactor will then take that event handle and call it. So this event demultiplexer is the core of the reactor. So how the operating system comes into play here. So this reactor will this event demultiplexer will listen on an event source. So this event source is provided by the operating system. So you can have different event sources like network, pipes, files, which all produce events, and operating system also provides you file handles. So resource handles which identify each event source. So what the synchronous event demultiplexer does is it listens on this event source which are set by the reactor to it, and it will look up this event source and call the correct event handler. Okay, so and what the application does is the application interacts with the reactor over a reactor API. So what the application does is application will first register. The first thing application has to do is implement some concrete event handlers. So there are so for example, we will see some examples of this so that it becomes more clear. So from the application point of view, like for example, I'm writing this edge server, what I need to do is I just need to implement some event handlers for the events coming in. And then I register these events with the reactor. And when the reactor and start this event loop, which is the demultiplexer. And as soon as the event comes in, the reactor will call the right event handler. So this is what basically a reactor does. So let's dive into some examples to see how the reactor works. So as I mentioned, the main components are synchronous event demultiplexer, reactor interface, reactor resource handles, and application. So I described them just now. So I'm moving on. So let's see what an application does. So the application, from application point of view, first you implement some concrete event handlers. Then you instantiate a reactor. Then you register your event handles with the reactor. Then you start the reactor event loop. That's it. I mean, there is, because the reactor is sequentially handling the events, there is no race conditions. There is no need of threads. So now we have seen what is a reactor. Let's try to design the same edge server using a reactor. Any questions we have? I think so the question is the operating system an ordinary one or real-time operating system? The operating system on which we were running, we were supporting both non-real-time and real-time operating systems. But for a reactor pattern as such in general, it need not be a real-time operating system. It can work well with different operating systems. So edge server using a reactor. So let's try to design the edge server. Okay, so what we are going to do is we have used ePOL. So I think we have one ePOL. So ePOL is a mechanism similar to select or poll and it's very specific to Linux. So ePOL is our event demultiplexer. So what ePOL does is you give a list of file descriptors to ePOL, which is called watch list, and ePOL will look for events on that file descriptor, and if it sees some event in the file descriptor, it will basically exit the event loop and give the return you the file descriptors on which the event occurred. So that's what ePOL does in short. So we are going to use ePOL as our reactor, and we build a reactor interface around ePOL. So what the application does? So what the application does is application first, as I mentioned before, application will implement the event handlers. So in our case, it will implement the sensor event handlers. For different sensor, we can have a different event handler. And this event handler will take care of the protocols to communicate with the sensor. And we will also need to implement the server broker handler, which will also implement the protocol to communicate with the server. So once we implement this concrete event handlers, we register these event handlers with the reactor. So once we register the event handlers with the reactor, then what the application does is the application starts the ePOL loop and then waits. So as soon as what the reactor does is, as soon as it receives any event from the sensors or socket, it will dispatch that event to the correct event handler, and the event handler will then take care of whatever needs to be done with that event. So these dotted lines show that the actual data is read by the event handlers, and the data sent to the central server is done by this broker handler here. That's what this dotted line shows. But the actual management of the socket, or the socket listening on the socket, is done by the ePOL. So the load on the application is kind of moved to the reactor. So the application becomes quite simple and straightforward. So I have done a basic a small implementation which is available in the GitHub, sorry, and there's a link. So here anybody can go there and look at the implementation, and if you're using ePOL already in your code somewhere, you can take inspiration from here. You can use this ePOL to kind of implement the reactor pattern. So let's see the code, how it's implemented. So this is the event handler interface. So this is the abstract interface. So here we have parameterized the handle type and event type. This is because in our application sometimes we use a 0MQ, and the handle type and an event type of 0MQ message queue is different. So depending upon what kind of event sources or what kind of reactor, what kind of event handler you are using, the handle type and event type can be different. So that's why it's parameterized. Then you have this virtual functions, which the concrete event handler should implement, which is handle event and get handle. So for our use, in this context, we're using ePOL. So we have created an alias for ePOL handler interface, which takes the event handle is a file descriptor, which is an int, and the event type is it's a uint32 type flags, which ePOL uses. So we have created an alias. So we will be using this alias in our reactor. So next, So this is our sensor handler for our IoT example. We need to implement the sensor handler, which inherits from the handler ePOL handling interface. And we need to implement these two functions, these two methods. So let's see a simple implementation here is, so when this sensor handler will be dispatched, you will get the event which caused the event demultiplexer to dispatch this. So we first check whether it's input event. Then we can read the data, and then here you can do write. You can add the code to write the data to the central server. So so that's the handler on the application side. So in the reactor, so ePOL reactor is our reactor interface class, which actually uses ePOL to implement the reactor pattern. So it's a resource class, so you follow the rule of 5 because we need to have a destructor here. So I'm not going to go into the detail of this rule of 5. The important thing is these 3 methods. So method, so you the application, you use this register handler method to register event handler. You can remove the event handler and then handle events. The handle events is the call which actually starts the event loop, and this is a blocking call. So this will block the event loop, and till the event there are some events. Basically, this call here will block indefinitely as long as there is a register, there is a handle registered with the reactor. So now let's see a sample application. So in the sample application, instead of network sockets, I'm using a FIFO. It's a Linux FIFO. So what the application first does is it sets up a FIFO. It's instantiates a reactor. It's instantiates a concrete handler to handle the sensor data. Then I'm using catch to a unit test framework. So it's a check. Basically, I'm registering the handler with the reactor, and then so this is just to simulate a sensor. So there is a simulator which just sends data over that pipe, FIFO. So I start the simulator and then handle events. So this handle events typically blocks, and this will be blocked until there is some event handler is registered with this. So it will be blocked. So in a real application, this is all your application does. So it blocks and it waits for the event. As the events come, the reactor will call the registered event handler, which will handle the data. So that's all. That's all to the application. But because this is a test, what we have done is whenever there is a event, the handler actually deregisters itself from the reactor, so that the reactor loop can exit, and we can check whether we have received the correct data which we sent. Okay, the complete code is in the GitHub. You can take a look. So some of the design observations. Do we have any questions before we go into some design observations?
So it looks like another question just came in from Shashank.
Yes.
He asks, so as I understand, the polling algorithm can service only one sensor at a time. And if UDP protocol is used, won't this lead to lost packets and in turn lost sensor data?
No. So what actually happens is, so ePOL, the implementation here which you're using ePOL, it has an event queue. So and the network stack, Linux network stack also has some event buffer, data buffer. So whenever a socket, whenever UDP socket becomes ready to be read, I mean, which has some data, that FD becomes active and ePOL queues it till somebody reads the data from it. And depending upon the network buffer, UDP buffer, the data will be buffered there. And when the reactor will call the event handler, which will read the data from the FD, you will get the data. So the packets will only be lost when there is too many too many different events, and event handler is taking longer time to process the data. Then of course the packets may get lost. So we will see about some of the limitations of the reactor in the subsequent slides. But yes, but as long as there is reactor is running without blocking the event loop, you should not see any packet loss. Okay. And thank you for the questions, by the way. So some of the design observations. So here we see that the main advantage of reactor is its simplicity. So if you notice, from the application point of view, all you need to do is implement some concrete event handlers and start the reactor. You don't have to do anything else. So the code becomes extremely simple and straightforward. So this is the major advantage of Reactor. And the other advantage is because of the simplicity and because of there are no threads and no synchronization requirements. Typically, in a single core processors, the reactor performance is typically much better than a threaded application. So there is that's another win for Reactor. And again, the second important thing is adding support. If you want to do some different protocol or something else, all you need to do is inherit. You just implement the abstract. You just implement a concrete reactor. A concrete handler, and then you are done. So that's again an advantage of using a reactor. And another key observation is to have a mental model of this reactor. So this is sometimes a bit difficult when you start with reactor. So if you notice what the reactor what the edge server application does is, from the application point of view, it just registers your handlers and starts the event loop and just sits there. The program flow is controlled by the events coming in. It's not controlled by the application main. So there is, this inverts the program flow. This is also called the Hollywood principle. It's because in Hollywood, when you approach some agents, you just give your contact details. You don't call them back, they will call you. So it's like that. So it's a Hollywood principle. So the application will not keep on checking whether there is something for me to read. The reactor will call the event handler when there is something to read. So this is good to keep in mind. This is the mental model I use when reading on the reactor code. So let's, though the reactor is simple and has these advantages, there are some limitations of reactor pattern which we must keep in mind. So the major limitation comes from its actual advantage, where the reactor it uses this synchronous event demultiplexer, which essentially it's a serialized way of event handling. So you have events, each event is addressed serially. So which means that one of the questions which was asked earlier is comes into play, where if there are large number of events coming in, and the event queue will get filled up quickly, and you may not able to address handle all those events in a fixed time. So This is one of the limitations of reactor pattern. The second limitation is the event handler. So you cannot do anything in the event handler which will kind of which is more CPU intensive or which is long running, because it will block the event queue. So suppose there is an event handler which is kind of doing some number crunching, or which is kind of doing something which will take long time to complete. So what will happen is, till that event handler has completed the task, the reactor cannot call the next event handler because it is processing the events one by one. So it will halt, it will block the event loop, and you will start seeing problems. The third is, of course, reactor is single threaded and it executes on single CPU, which has its advantages, but sometimes you have a huge CPU or huge amount of computation power with you, and you kind of want to use everything in that, and reactor is not the best pattern to do that. So if any of these limitation is kind of becoming a bottleneck for an application, then probably you should look at some other concurrency pattern which is more suitable for your application. But I will recommend that you can, whenever you design a server client based on concurrent system, consider reactor pattern. Then because of its simplicity, because if it's able to fulfill your needs of the design, then it's the one of the very good patterns to use. Because reactor pattern is so easy to use and so widely applicable, you will see reactor libraries in all the major languages. You will have something, some reactor libraries. And also, though in the GitHub, I have implemented my own reactor using EPOL. That's just to show how it's done. But typically, when you're using the production code, you will use a reactor library. So for C++, I think a very good reactor library, Poco is a framework, C++ framework, which provides a reactor library also. In Rust, you have Tokayo reactor, and Java, you have project reactor. So these are the reactors which I have worked with, and I have seen there are many more reactors. So I just listed some of the reactors which I have worked with. Out of this, I think libuv is the I feel this is the reactor which is extremely performant, and this forms the core of Node.js execution model. So it's a very good library or framework which you can use. So before concluding this, I think one point I'd like to mention, there is another pattern which is closely related to reactor, which is also an event handling pattern, and which kind of takes care of certain limitations of reactor pattern. It's called proactor pattern. But going into the details of proactor pattern, it's a different talk. And many of these libraries support both reactor and proactor pattern. So I think I have come to my end of my presentation. So thank you. Thank you, Sly. Special thanks to Rogniron for reviewing it, and Ankur Sattli, of course. And thank you everyone for attending. And I think we have some time for Q&A.
Right, so we have a question, which is basically, can you share the GitHub link?
Yes, it's in this presentation. I think this presentations will be shared. So you can, in this presentation, there's a link, but I can put the link in Discord server if you.
Okay. So If anybody else has any questions they'd like answered by Selvakumar, please feel free to use the Q&A tab to ask your questions now. Let's give it a couple of minutes if friend has any questions. Otherwise, thanks for the great talk.